In this video, we're looking at conservation of energy for what we call ideal systems. More on that in a moment. We want to figure out a formula for gravitational potential energy and then use that in our conservation relationships. We already know how to talk about kinetic energy. Motion causes objects to have this, and so we've got a formula for that. We also know how to quantify stored energy in a spring, which has to do with the work done on the spring to compress or stretch it. We can do a similar thing with gravitational potential energy. If you think about the work required to lift something up in the air, you have to apply a force at the very least equal to the amount of its weight in order to lift it up in the air. And as you lift it up in the air, you do work, and that work is stored as gravitational potential energy. How do we know the energy is stored? Well, you can get it back as kinetic energy if you drop it, right? So that's how we know. Now, our formula that we come up with gravitational potential energy comes from the fact that the minimum amount of force required to lift it is equal to the weight. And if we lift it at a constant speed, then those two forces will be the same. So the work done is equal to mg, the weight of the object, times h, the height you lift it up. And that all works out. That gives us units of joules. But this is really only good if little g is a constant near the surface of the Earth or another planet where you know little g on that planet. And m is pretty obvious. We know what the mass of an object is. But what about h? Where are we measuring our 0 point? It turns out it doesn't matter. You can pick 0 to be whatever you want. And in fact, as we will learn in a more complicated version of this a little bit later, infinitely far away from the center of a planet is where we call 0 when we're dealing with gravity in very large scales. More on that later. But we can pick the ground to be height 0. We could pick the height of a table to be height 0. We could pick the starting point to be height 0. Whatever makes your problem easier. So for example, a 50 kilogram woman stands on a diving board 1 meter above the water. What is her gravitational potential energy? With respect to the water, it's mgh, or 500 joules, 50 kilograms times 1 meter times 10 meters per second squared. But what if the pool is actually on the top of a building, right? This is a rooftop pool. And we now are going to ask, well, what's her gravitational potential energy with respect to the ground? Well, if the ground level is h equals 0, then mgh gives us 50 kilograms times 10 meters per second squared times 10 meters high, which gives us 5,000 joules of gravitational potential energy with respect to the ground. What if she falls into a 5-meter deep pit off the side of the building, right? Hopefully she's okay and lands on an airbag or something. Very impressive stunt actor, right? Well, if we call 0 the ground, then now she has negative 2,500 joules of gravitational potential energy, right? Less than she would have had at height 0. And so this is to illustrate that where you call 0 doesn't matter. It's okay to have negative gravitational potential energy because it still works. If you were to climb out of that pit, you would gain potential energy, right? Spring potential and kinetic energy can't be negative because of the way they're defined in terms of speed squared and displacement from equilibrium squared, but gravitational potential can. Does it matter how she gets into the pit? Not really, right? She could fall into the pit. She could climb down the ladder and walk into the pit. The result of how much energy she has at the bottom of the pit is the same either way. There's another thing to think about. You've probably heard of this demo in class. We may watch a video of it because I don't have the bowling ball set up. But why is the professor sure that when they release the ball from right at their nose, stand perfectly still, that the ball won't swing back and knock them out? Well, the reason for that is that energy is conserved, right? Energy is never created or destroyed. Unless you give it a push, do work on it to speed it up faster than it would go normally just by being released, it can only come back up to the original height. So let's look a little bit more at energy conservation. If you imagine some mass, some blob, right, and it falls down. If energy is conserved, where did it go? Because after it hits the ground, it's at rest again. It started at rest, had gravitational potential energy up there, then it sped up, and then it hit the ground. Well, it turns out that when things suddenly stop or when things are slowed down by friction or something like that, conservation of energy still applies. It's just no longer mechanical energy. It's no longer potential and kinetic, right? Joule, after whom we name the unit of joules, did some experiments where he allowed gravitational potential energy to pull a weight down slowly and pull a rope that was attached to this device. This was filled with a fluid. And basically, the motion of all of this, which eventually got slowed, right, because it was against the resistance of the water, he was able to measure an increase in the water temperature. So ultimately, when you lose gravitational potential energy or you lose kinetic energy, and it seems like it has been destroyed, usually what happens is it became heat or a transfer of thermal energy. Right? So when we talk about conservation of energy in our class, we're really talking about conservation of mechanical energy, which includes kinetic and potential. And so energy is conserved, no exceptions. And there's two types of systems. Ideal systems, where just these three terms we've learned about are enough, or there's non-ideal systems. And we're going to focus on ideal systems right now, but we will say that any time that's violated, that probably it's thermal energy or heat. So mechanical energy, I've already said this word a few times, or this phrase a few times, and it's really just the sum of all the kinetic and potential energies that we have. So chemical energy, thermal energy, things heating up, mass energy like E equals mc squared, those things are not mechanical energy. They're still energy, and they're still part of the energy conservation conversation, but they are not mechanical energy. And if a system is ideal, that is, there's nothing non-conservative going on, more on that in a second, right? We can say that the initial mechanical energy equals the final mechanical energy. The kinetic energy plus the gravitational plus the spring at the beginning is equal to that at the end. They do not gain or lose mechanical energy. And the reason for this is that all of the forces that are involved, spring force and gravitational force, are a special type of force we call conservative forces. The kind of things where only gravity acts, a projectile, even a frictionless roller coaster. We have normal force, which isn't a conservative force, but on a roller coaster, it always acts perpendicular to the motion, so it does no work. The spring-loaded cannon, because a spring applies a force in a way that's predictable and understandable. So these different forces acting on the object just work to transfer energy around to different conservative or mechanical forms. So if you look at a projectile flying through the air, and we've analyzed this before, right? What forces do work on this projectile? Well, it's just the force of gravity pulling straight down. That's the definition of a projectile, right? Ignore air resistance. And so that means any gravitational potential energy you have, it can become kinetic energy or vice versa because the force of gravity is pulling down, right? Initially, it's fired upward, right, with some kinetic energy, and gravity is pulling down, doing work to slow it, so transferring from kinetic energy to gravitational potential energy. And then once it reaches its peak, it all gets transformed into kinetic energy. So for example, right, if we start at 20 meters, this is a 10 kilogram projectile, so it's 2,000 joules of gravitational potential energy. If we go up to 40, it's 4,000, back down to 30, 3,000, 2,000, 1,000, and 0 joules when you hit the ground. And since the total amount of energy of mechanical energy is kinetic plus potential, we need to calculate that kinetic energy at the beginning, 1/2 mv squared, which is 4,500 joules. Well, now we have a total of 6,500 joules, which means the kinetic energy has to add to the potential to get to 6,500 joules. So at the bottom of the flight, when all of our energy is kinetic, it's going the fastest it goes just before it hits the ground. It's 6,500 joules of kinetic with 0 joules of potential, right? And so we can ask ourselves other questions about this. Once we know the kinetic energy at the top, we can use kinetic energy equals 1/2 mv squared to solve for the velocity. And we find that at the top, the speed is 22 meters per second. We already know that at the highest point, the velocity is parallel to the ground. It's all in the x direction. So we know everything we need to know about this problem. We can also do this kind of thing on a roller coaster, right? What forces act on the ball? Force of gravity and normal force. But only the force of gravity does work because the normal force is always perpendicular to the path of motion. Which means the force of gravity, just like the projectile, helps transform between gravitational potential and kinetic. And we can figure out things based on what we know. If I tell you we start with 1900 joules of energy at point A at the top, where it's at rest, that means that's all of our energy, right? What is the mass of the ball? Well, we can solve for mass by dividing gravitational potential energy by GH, giving us 2 kilograms. Then we have everything we need to know to solve for the rest of this problem. We know that we start at rest, 0 kinetic energy, and we have 1900 joules of gravitational potential. As it goes down the hill, right, we get more kinetic and less potential until we are at the bottom where we have all kinetic and no potential. So how do we approach this kind of problem? What you do is you start by stating initial mechanical energy equals final, and that means kinetic plus gravitational plus spring equals kinetic plus gravitational plus spring. We have to decide where the initial and final are. We get to pick our 2 points. Ignore what goes on in the middle because that's not important for this equation. Take a picture of what's happening right in that moment. Is it moving? Is it up high? Is there a spring? If you can answer yes to any of these questions for either the initial or the final, then you keep that term. If it is not moving, the kinetic is 0 and you can cross it out. If it's not up on the high, if it hasn't been lifted up or down throughout the process, then the gravitational is the same at the beginning and the end, and you can cancel those out. If there are no springs or the spring is not compressed or stretched, those could be 0 as well. Get rid of anything that's 0, and then rearrange, simplify everything, isolate the unknown, and finally plug in your numbers. Most of these terms, well, gravitational and kinetic both have mass, so oftentimes mass will cancel out of one of these equations, which is nice, so we can simplify things that way. So, example problem. A spring-loaded cannon, it's not really a cannon, but you get the idea, it looks like a cannon, with a spring constant of 15,000 newtons per meter is compressed 80 centimeters and released, firing a 60-kilogram circus performer into the air. How high is she when her velocity slows to 10 meters per second? So we start with our conservation of energy equation. Initially, we'll call height at the beginning 0, which means gravitational potential energy starts at 0. We start at rest, so kinetic energy is 0. We only have spring at the beginning. At the end, there's no spring because it's been uncompressed. And so we can rewrite our equation with all the variables there. 1/2 kx squared is mgh plus 1/2 mv squared. Solve for h, plug in our numbers, and we end up with 4.6 meters. That is how high she is when her velocity is at 10 meters per second. When you think of a spring hung vertically, and we did this demo in class the other day and let it bounce up and down, and I sort of did a couple of things that you might call a cheat. I made it so that we were measuring 0 force when the mass was hanging on it at equilibrium, because that would give us a simpler idea of the spring. But there's a lot that can be done with a spring, and so we want to kind of look at that. So if you imagine a 1 kilogram block is placed on a spring and compresses it 10 centimeters. Now, because it's on top of it and not just a horizontal compression, it didn't just change the compression of the spring or the delta X. It also changed its height, right? Then it gets pushed down an additional 20 centimeters. Then how high does it go when it's released? So there's a lot of things here that we have to think about. So the maximum height that it goes after it's released is really what we're looking at. How far from its lowest point would be a way to do it. You could also do this from some other reference point, but there's no real reason to do that. First, we need to find the spring constant. And in order to do that, we can just use the modification of Hooke's law that says the applied force that compresses the spring is equal to kx. In this case, we placed a block of 1 kilogram, so that's a 10 Newton block on a spring, and it compressed 10 centimeters. So that gives us 100 newtons per meter. Once we know that, we can go on for the rest of the problem. But I want to make a point here. If you wanted to try and find the spring constant by using conservation of energy, mgh equals 1/2 kx squared, this is incorrect. And it's not immediately obvious, I think, why it's incorrect. But the reason it's incorrect is in order to compress it, we're basically letting it be at equilibrium. And in order to do that, if you just drop that block on it, it would bounce up and down for a while and eventually come to equilibrium because of air resistance and thermal dissipation in the spring and some friction and that kind of stuff. And that is work done by something. And that's not in this equation. So that's why this equation doesn't work. So it's very important to remember that when we set something in equilibrium, we apply a force, and we see that something is compressed in a spring, that's a Hooke's law situation. When we let something go and be released and let it move freely without putting something like a hand in there to mitigate it, then we're talking about a conservation of mechanical energy problem. So now when we're talking about releasing it and letting it spring upward, that's what we're looking for. So we know we start with spring potential energy, and we're going to call the height that it's at the beginning 0. So we can say there's no gravitational potential energy, and our interest is in the point where it reaches its highest point, which for vertically launched, free fall problem will be when the velocity is 0. This now is 1/2 kx squared equals mgh. And this is why, another example of why this is not an okay equation for the previous situation. The previous situation was not drop a block and see how far down it gets compressed before it jumps back up. It was at an equilibrium situation. So in this case, we have height 0 at the starting point, height final up there. Kx squared divided by 2mg ends up being our relationship when we get about 45 centimeters. So another question you might ask is, when is it going the fastest? And this is not the most obvious answer necessarily, because it's certainly at rest at the top, but it's also at rest at the bottom. So it speeds up and then it slows down, right? The spring is accelerating it up, but then at some point, the force of gravity takes over and starts slowing it down. And so we need to figure out where it has its maximum velocity. There's a bunch of possibilities. Is it at the beginning? Is it at the end? Is it when you reach that point where it was at rest at equilibrium before, or when you reach the unstretched length of the spring? Where is it that this happens? Well, it turns out that it's at point C, where it was at equilibrium before. And the reason for this is when it's at that point, right, is that the net force when it's at B is the force of gravity, right? And as soon as the spring releases it, right, goes completely unstretched, then that's the force of gravity. But if, as we're going from C to B, the force of gravity is getting bigger. Well, it's staying the same, but the spring force is decreasing, and we're getting a smaller upward acceleration. And so, or in some cases, you would say a downward acceleration, because the force of gravity is bigger than the spring force. Only at C is the net force 0. And if the net force is 0 at that point, the spring force and the force of gravity, then the acceleration is 0. Before that, when it was compressed more, the spring force was bigger. And once it's above that point, the spring force is smaller. So we will get an acceleration either up or down. So this is the maximum velocity, right, at equilibrium. And this ends up being important. We'll talk more about this when we get into simple harmonic oscillators, mass spring systems, that the fastest the mass spring system goes is when the forces are balanced at equilibrium. All right. From D to C, spring force is bigger, so we have positive acceleration. And from C to B, we have negative acceleration. All right. What if the mass actually sticks to the spring? So what if we attach it? Well, then we get a slightly different scenario, because instead of, just being launched upward, the spring then stretches out. And of course, as the spring stretches out, we store energy again, right? So now the conservation of energy equation changes to have both gravitational and spring potential at the end. So we have a slightly larger equation, slightly more complicated. And the height we go up is the initial compression plus the final stretch length added together, right? So we now have an equation in terms of our initial and our final x. We're going to have to do a little bit of work to kind of rearrange that. We've got an x final and an x final squared, so we're going to need to use a quadratic to solve that. And we end up with possibilities of positive 10.1 meter or negative 30, and the only one that makes sense is the positive 1. And so we add that to our 30 centimeters, and our height is 40 centimeters above the lowest point. The negative solution is back when it was at height 0, which is the other option, right? That's when it's stopped as well. Either the spring hasn't been released yet, or it comes all the way back to it. So another way to look at this is if the equilibrium position is the height, then it goes up 20 centimeters or down 20 centimeters, and it'll oscillate between those 2 points. The other type of problem that we might want to look at is a circular motion and energy conservation problem. If you remember the turning point lab, we had to combine those two things together a little bit already. But here what you have is you're releasing something down a track, and then it goes up around a circle. And we want to know, how high do I have to release this thing from so that it just gets around the track? Now you might initially think, oh, just the height of the circle. But if it does that, then at the top of the circle, it will be at rest, and it will fall straight down. We need it to get around that circle. So we need to use what we know about circular motion, which is that the minimum speed to get around comes when the normal force goes to 0. And so the force of gravity is our centripetal force. We get V min as the square root of RG, something we've already solved from circular motion. And then we can say, well, we start with no kinetic and no spring. And at the end, we have both kinetic, because it's getting around the circle at the top, and we have gravitational potential energy. So we can take what we know for H minimum and find it using that relationship. We can also do this in the turning point lab. So that's the end of those couple of example problems, going around a loop, of course, and start again. All right, so there's a couple of example problems for ideal systems.